So welcome everyone. My name is Mary Ann Francis, and I am happy to welcome you to the third iteration of the Search Mastery Speaker Series for Spring 2022, where we explore the foundations and practice of search, skills, education, and literacy. And today we're really excited and happy to have Jordan Boyd-Graber here to talk to us about why we have computers answering questions from web search data and how can we do it better, and the controversy between the Manchester and Cranfield views. In terms of introduction, Jordan is an associate professor in the University of Maryland's Computer Science Department, the iSchool, UMX, and the Language Science Center. His research focus is in applying machine learning and Bayesian probabilistic models to problems that help us better understand social interaction or the human cognitive process. He and his students have won Best of awards from multiple professional associations and conferences, including the Conference on Neural Information Processing Systems, the Association for Computational Linguistics, and the ACL Conference on Natural Language Learning. Jordan also won the British Computing Society's 2015 Karen Spark Jones Award and a 2017 NSF Career Award. So I just want to welcome you, Jordan. We're really looking forward to your talk, and I'll turn things over to you to explain your ideas and thoughts in really fully. But just before I do that, I want to mention to the group that you're welcome to ask questions in the Q&A and in the chat. I will try and monitor them. If there's anything that's really topical or timely, I'll chime in for Jordan to respond then. Otherwise, I'll keep them all for the end, and we'll have a Q&A discussion toward the end of the talk. So thank you so much, Jordan. Over to you.
Well, and thank you for having me. So it's my pleasure to be here, and I will mention that this is the second time I've given this talk, so it's still a little rough around the edges. And in general, these ideas are relatively new, and I'm still trying to figure out how to present them well. So I'm really looking forward to interaction, discussion, and feedback here. So this is a little bit different from the kind of talk that I normally give. And I'm going to first start out by talking about something old that I had nothing to do with, something called the Cranfield paradigm. And many of you probably know about this, but for those who don't, I will review it briefly. And then I'm going to talk about what is not a new idea, but a repackaging of some old ideas that my students and I have worked on, and it's something that we're calling the Manchester paradigm. And then I'll talk about some of the insights that come out of this paradigm for interacting with question and search data, and how this can help us perhaps advance artificial intelligence. So let's jump into the old stuff first. And a lot of my presentation here comes out of ideas in the article, The Evolution of Cranfield by Ellen Voorhees, whom many of you know at NIST. And the Cranfield paradigm is named after a university in England, a very small university, but it has an outsized impact despite coming from a tiny, tiny university. It is the foundational principle that all of the major search companies are built off of. How did they know that they have a good search mechanism? Comes out of ideas developed out of a library in Cranfield. And Cyril Cleverdon, the librarian at Cranfield, wanted to develop a way of evaluating whether he had a good organization of data. And in the old days, when you just had card catalogs, you had a user study. People would come in, they would try to find stuff, you'd get their opinions, and from that, you would make a decision about whether your organization was good. And at the end of World War II, there were suddenly these computers and computational methods. Could those perhaps help you figure out whether you had a good organization of data and were able to fulfill people's information needs? And all of this happened at a place called Cranfield, as I mentioned before. It is unique in that it was the seat of aeronautics education in the United Kingdom. And it is unique in that it's one of the few universities with an airport right on campus. And he proposed the following way of evaluating whether you had a system that adequately met users' information needs. Rather than running a user study every time you had a new system, he proposed to have an automated index. And so rather than coming from the minds of librarians, he was thinking that you would just keep track of all of the words that appeared in your documents, and this could create an index. And there are different ways that you could match up queries to indices. How did you know if you had a good way of doing that? And what he proposed in this article was that you could figure out for a bunch of queries what were good documents that you could find for those queries. And the way of doing that he proposed was that given some query, what is the airspeed of an unladen swallow, you could find all of the documents that were responsive to that query. And then when a system highlighted some documents as an answer, you could compute something called the precision and the recall. How many were correct? How many did you find? And this gives you an instant evaluation of whether you did a good job of answering those questions. At the time, this was a really controversial way of measuring how good an index was. And there are a lot of false assumptions about this technique. One thing is that an answer for one person should be the same answer for another person, but that's obviously false. If I ask why the sky is blue, I'll get a different answer, or I should get a different answer than if my 5-year-old daughter asks, why is the sky blue? It also assumes that answers are static for all of time. Who is the president in 2016 has the same answer as 2017, 2024. And it also assumes that you can go out and find every possible document that answers a question. And so these are obviously false, but despite the obvious false assumptions in this paradigm, it was pretty useful. And it laid the foundation, as I said, for the evaluation of all of the search engines that came afterward and are now multi-billion-dollar companies. And one of the ways that Cranfield became so prominent is by the decades of work by Ellen Voorhees and others at NIST down the road in Gaithersburg. For decades, they put out Cranfield inspired collections so that people could come in, try out their new search engine, and see if they were answering people's questions well. And this has gone beyond just search engines. Reusable test collections have also become the foundation of artificial intelligence and machine learning. You may have heard about leaderboards for machine learning and artificial intelligence. Those same processes are being reused to create systems, and those systems are evaluated automatically in this way. The other big legacy of Cranfield is the focus on user data. And you collect a bunch of data from real users, but then you stop interacting with them. And one of the things that I work on a lot is how do you get computers to answer questions automatically? And one of the largest data sets for doing this is very clearly inspired by the Cranfield paradigm. They gathered a bunch of questions that people asked online, had annotators mark what the correct answer should be, and then packaged that so that they and other researchers could test out their question answering systems. And this clearly matches the Cranfield paradigm. Rather than marking individual documents as the answers, they're marking individual spans, but the idea is the same. You have a reusable test collection that you can figure out if your question answering system is working well. Okay, so that is the first part of my talk. I will pause if there are any questions, issues, commentary that people want to share. And if not, I will move on to the next phase when I will talk about an alternative to thinking about search in this way.
Jordan, I don't see any questions yet for you.
Okay, all right, so pressing on, let's talk about an alternative to the Cranfield paradigm. This came out of some ideas developed by my former student, Pedro, who helped come up with this idea of an alternative that we're calling the Manchester paradigm. And so because this is new, we need to justify why we're calling it the Manchester paradigm. And so Manchester, like Cranfield, is a university town in England, but that's not enough. There are three big reasons why we're calling it the Manchester paradigm. And one reason comes from mythology, one reason comes from game shows, and the best reason that we're saving for last comes from the computer science pioneer, Alan Turing. But we're saving that one for last, so let's start with the ones that are a little bit more of a stretch first. Okay, so first, during the 19th century, the Manchester Regiment of the British Army used the Sphinx as their insignia. And there's a connection between the Sphinx and question answering. You may remember from mythology that the Sphinx sat outside Thebes, and whenever someone came by, it would ask them a question, and if they couldn't answer the question correctly, they'd get eaten. And so the Sphinx asked Oedipus what starts out on 4 legs, then goes around on 2, and finishes up on 3 before it's through. And the answer, of course, is a man. And this isn't just an idle question. If you know the story of Oedipus, you know about I don't want to spoil the story for those who don't know it, but it reveals something about his history, the course of his life. And in understanding why the Sphinx asked him that question, he was able to understand something about himself. In a very lovely commencement address by Dana Burgess connects the idea of asking people questions to getting people to be able to think critically. And he connects this to education, the role of professors, and professors often ask weird questions on exams or in the classroom as they're using the Socratic method, and they're not trying to figure out the answer to a question. The reason that they're answering these questions is to help you, the person being asked the question, to think critically. And that's reason number one why we're calling this alternative to the Cranfield paradigm, the Manchester paradigm. Sometimes people ask questions not because they want to know something, but because they want to see how you think. And this obviously has a connection to education, what many of us are involved in. The second reason for calling this the Manchester paradigm comes from a game show called University Challenge, speaking of higher education. And this was a game show started in the 50s in Manchester, England at Granada Studios. And the host of the show asked questions. So this is Bamber Gascoigne, and he would ask questions to 2 teams of university students. And these questions are weird questions. Let's see an example of this. This is a technically it's seeking information, but there's no question mark here. And it's written very weird. So let's take a look at some of the stuff that's going on here. And so at its premiere, the librettist of this opera portrayed a character who asked for a glass of wine with his dying wish. So this is a reference to a character and an actor, but neither of those people are mentioned by name. The librettist is Emil Schikaneder. He's not mentioned by name. Who asked for a glass of wine is a character, that's Papageno. And if you know opera really well, you'll be able to say, aha, yes, this is actually the magic flute. You'll also notice that the question has other complicated stuff here. It has a reference to a main character in this opera, a man, and you only realize later that this is Tamino. Why is this question written in such a weird way? Because it is designed to test contestants' ability to answer questions. And it's designed to reward people who know more about a topic to be able to answer sooner and to beat the other team and to get more points. And this is called a pyramidal question, that it starts out really difficult at the beginning, and then at the end of the question, it's getting pretty easy. And so maybe you don't know a lot of opera, but maybe you can make the connection between an enchanted woodwind instrument and the magic flute, and you'll get that correct. And so in the chat, it's very rightly pointed out that if you have the end of the question, that is correct, but you don't see all of the question at once. It's given to you word by word, and it's a race between the two teams. As it's being written out, you need to figure out when do you have enough information to answer with high enough probability. Okay, so moving on to the third reason to call this the Manchester paradigm, Alan Turing. Alan Turing, while at the University of Manchester, proposed a way of testing whether a machine were intelligent based on what he imagined could be a Victorian parlor game, where you have an interrogator who is paired with one of two intelligences or potential intelligences, and one could be a human, one could be a computer, and he, as the interrogator, as Alan Turing wrote, needed to figure out which one was human and which one was a computer. And the way that this was uncovered was through asking questions. And these questions could be about anything, but they were probing questions. They were artfully designed questions. And some of the things that we've seen that came after the Turing test called themselves Turing tests without the skilled, knowing, probing inquisitor. I'm focused entirely here on the original definition of the Turing test, where the interrogator was skilled and was asking probing questions and not just chit-chatting idly. Okay, so just to wrap up our conception of the Manchester paradigm, how do you know if it's a Manchester paradigm question? Was the question written with skill? If it is, then it's a Manchester paradigm question, a question written for a game show, a question written for an exam, a question laser focused on determining whether you're talking to a human or a computer. Does the questioner know the answer? If the questioner knows the answer, it's more likely to be a Manchester paradigm question. It's not information seeking. And can the questioner evaluate the answer? In the Cranfield paradigm, where people don't know the answer to a question and they get an answer back, maybe they have some idea whether an answer is reasonable. If they ask, what is the population of Canada, and you get the answer 3, you know that's probably not right, but can you say whether 15 million or 50 million is more likely? In the Cranfield paradigm, probably not. In the Manchester paradigm, the inquisitor usually knows the answer. And one thing that I want to stress here is that skill is talking about only the way the question is written. It doesn't refer to the knowledge of the person writing the question. In the original Cranfield experiments, these were about metallurgical experts trying to figure out what's the right metal to put in the Rolls-Royce engine for a jet. And so these people were really smart, but they didn't know the answers to the questions that they were writing. It was the Cranfield paradigm, but in a very niche subject. Okay, all right. So that is our proposal for the Manchester paradigm. And so I am happy to pause for questions. I'll take a look at the questions that came in on the chat. And so, yes, Dan made some good points there. So like the pyramidal question only works if it's read out loud, or in the case where deaf teams like from Gallaudet University are on University Challenge, it's put on the screen one word at a time and you still need to interrupt. So that's the only way that that works. Other comments, questions, witty remarks? Okay, so having proposed the idea of the Manchester paradigm, what are some of the benefits that can come out of this? This is a paper that I wrote while on sabbatical at Google Zurich with my collaborator, Ben Berginger. And here we're talking about some of the good things that maybe the Cranfield paradigm could learn from the Manchester paradigm, in particular, trivia nerds who are part of the Manchester paradigm. And so since I was at Google, one of the big traditions of Google is a process called dog fooding. You try out stuff before you ship it out. And this is what trivia nerds do when they're writing questions for consumption. They try to answer the questions themselves. And this is one of the things that we did in the process of writing this paper. We tried to answer ourselves the questions that came in the Google Natural Questions dataset ourselves. And if you find problems in that process, that can help inform your data collection and data curation process. And since the release of the various question answering datasets like Squad and Natural Questions and Drop, a lot of papers, Weissenborn et al. Is just the first among dozens, have pointed out problems in the data collection and shortcuts that systems could take to answer these questions without really having to think about what the answer is. For example, there's a question answering data set called visual question answering. And if the question has, is there a, and you can just look at that and answer yes, without looking at the picture, without looking at the rest of the question, and you'll be right most of the time. So let's see how some of the norms that go into writing questions in the Manchester paradigm might be able to improve the kinds of questions that you get out of the Cranfield paradigm. And so we'll look at some examples from natural questions here. This is, we're not the only ones to have noticed this. C1 Min et al. In the ambig-QA dataset pointed out some of this stuff as well concurrently with what we noticed. And so here are some questions here. When was the last time Michigan won the championship? What year did the US hockey team won the Olympics? The Cranfield paradigm sometimes has grammar mistakes. And which Supreme Court judge has served in an international court of justice? So anyone see any problem with these questions? And here are the official answers from the natural questions dataset down below. I know it's hard to get interaction in a virtual talk. I presented this talk on Monday at Penn, and it was great to hear people shouting out the answers. And so if anyone wants to try to, okay. Yeah, so it's ambiguous, but how? Aha, yes, exactly. So third question, which country's Supreme Court? Yeah, exactly. And so one of the biases that you see in natural questions is that the answers usually come from English-speaking data. And so India has an example of this, but there are other countries as well. And yes, absolutely, the answers change over time. These all assume that what is the answer in 2018? Let's see. Yeah, so for Michigan, which Michigan is this? So like this assumes that it's Michigan's men's football team, but Michigan State won the women's cross country in 2014. That could also be an answer. What year did the US hockey team win the Olympics? So the men's ice hockey team won in 1960 and 1980, but the women's hockey team won ice hockey in 98 and 2018. Field hockey is also an Olympic sport, but the US has never won that. So I guess it really doesn't matter. And then Kotaro Tanaka is arguably much more historically important than Dalver Bandari. He was the Chief Justice of Japan as it was developing into a liberal democracy. And he helped create a lot of the legal structures that are now part of the Japanese legal system, the modern Japanese legal system. and then went on to serve in the International Court of Justice. So not to diminish the accomplishments of Dalver Bhandari, but Kotaro Tanaka is probably a more salient example that actually answers this question. But if you just use the natural questions dataset directly, that these are the right answers, Kotaro Tanaka is just as wrong as if the system had answered Judge Wapner. And so if you're training system to answer these sorts of questions, you will perpetuate the biases as mentioned in the chat. And maybe we don't want to do that. And so this isn't what happens in the Manchester paradigm. In the Manchester paradigm, because the person writing the question knows the answer, they have a mental model of how people might answer the question and push you away from doing that. So here's a question about, yeah, anyone know the answer to this? While waiting for that, Sherlock Holmes also lived at 221B Baker Street. And so it's saying, hey, you might think it's Sherlock Holmes, but no, I want a different answer. Yeah, Dr. Gregory House, that's right. And you might, if you know that this is a TV character, Arlie Ermey also played the father on of the janitor on Scrubs, but no, it's not that either. And so this is saying, here are some things that might distract you, but that's not the information that I want. And so this helps people train themselves to find the answer that is actually looked for. And it's not just a binary, this is wrong, this is right. Some answers are more right than others. And so here is a question where the official answer is potential energy. But if you just say energy, that's kind of right, but it's not exactly the concept that they're looking for. And so it explicitly says that if someone says energy, that's mostly right, but prompt them for additional information. If someone, but it's not just arbitrary words in that answer. If someone says potential, that's a different concept entirely. Don't take that. And you might think, this is just noise. Like, to have a big enough data set, it'll cancel out. And some of our former team members at Google looked at this. And if you have a human in the loop, you can improve the quality of the evaluation and better discriminate which system is better. And so if you're trying to decide, am I going to use this system to answer questions or this system to answer questions, if there aren't enough answers in your data set and you can't trust the evaluation, you can't know the answer. And so you could just say, well, who cares? We'll make a bigger data set. A recent paper that I had with a really fantastic undergrad, a sophomore student, Chung Lei, showed that if you pay more attention to the answer evaluation and the answer equivalence, you can also improve the systems during training. So that's our pitch for engineers, why you should care about this. But just from a fairness principle, you should also care about this. Okay, there's also some mathematical arguments about this. We argued through a simulation that you need a particular number of questions that separate the top system from the next best system. There's some math here, so I won't go through that as much here. If you're actually interested in this, you can look at the paper. But the takeaway here is that if you have these sorts of errors, ambiguities, and not enough discriminative questions, you need a much, much larger data set than even, say, natural questions to reliably decide what is the best system for answering these questions. Okay, and this is not just an abstract discussion here. More and more in the machine learning literature, we have been moving towards a leader-based mode of development and evaluation, for better or for worse. So the papers that get citations, researcher teams that get money are the ones that win these leaderboards. And if the data are imperfect, the outcomes of the leaderboard evaluations are also going to be imperfect. So can we do something, taking inspiration from the Manchester paradigm, to improve how the winners of the leaderboard are actually determined? But before I go into that, I will pause for any questions, commentary, or witty remarks. Okay, seeing none. This is again work by Pedro, whom I mentioned before. And this is inspired by an example of the Manchester paradigm that many of you may hate, standardized test. This is the first scholastic aptitude test from 1899. And standardized tests, for all of their faults, have some interesting math behind them. The idea of a standardized test is that the score that you get after sitting in this room with a bunch of sweaty people is comparable across time and place, that the skill of the person taking the test can be calibrated even though they answered different questions. And the score that you get out is based on how you answered many different questions. And this is getting even more complicated today with computer-assisted testing. And hopefully you can see this is kind of like a leaderboard. In a leaderboard, you're still ranking people, but the way that a lot of leaderboards rank the systems is just on the raw accuracy. And one of the insights of the Manchester paradigm is that not all questions are created equal. And you might need to do some analysis to actually standardize these scores so that you could compare person A taking a test in March versus person B taking a test in June. And one of the reasons that I think this hasn't been as adopted in the development of systems for answering questions is that you can wipe the memory of a computer. You cannot do that with a human, at least not yet. And so you need to have some mechanism for, even if you test people on different questions, be able to compare them. And so I want to say that there are plenty of problems with the questions that standardized tests ask and the implicit duopoly that has developed in the American educational system. All of those are problems, but just the math is separate, developed in a separate building in Princeton, New Jersey, from all of the other stuff that you may not like. And the hope is that maybe we could take some of the insights from the Manchester paradigm, people crafting questions over many years and developing techniques for analyzing the results of those questions that get answered, to make a better assessment of what system is better at answering questions than another. So let's go through a little bit of the math and see how this might help us with computer question answering. So leaderboards, as is, assume that questions are equally informative. And so we're going to change that. We're going to make some questions worth more than others in computing your score. And we're also going to explicitly estimate the skill of every participant. So just for explanation, let's say that we have two people answering questions, Ken and Bert. Ken is much better at answering questions than Bert. And so when do we learn something as they answer questions? And so if they both get a question right, that doesn't tell us much. If they both get a question wrong, that also doesn't tell us much. In the first case, the question was perhaps too easy. In the second case, perhaps too hard. It's where you actually have a split that it's more interesting. One of them gets it right, the other one gets it wrong. So mathematically, the way that we're going to do this is we're going to pass a real valued number into this function here that turns it into a probability. And there are going to be a couple of numbers going into this, but the first is just the skill of the system, player, agent, however you want to think about this. And so Ken is higher, more positive than Bert. And each question also has a difficulty. And so you just look at the difference between the skill and the difficulty to get a number, and then you pass it through this function, and it becomes a probability. So if the difficulty is exactly equal to the skill, then it's basically a coin flip whether you'll get the answer right. The more your skill increases, the higher the probability that you'll get it right. There are some additional parameters that we can put into this to model this better. One is the feasibility. And so the feasibility just acts like a vice. And as you increase this, it pushes down the probabilities. And this corresponds to the ambiguous questions that we talked about before. The less feasible a question is, no matter how smart you are, you can't get it right. If the question is, what is the capital of Georgia? And it doesn't say whether it's talking about the country or the US state, you either have to guess Tbilisi or Atlanta, and it's a 50-50 chance. No matter how good you are, you can't get more than 50-50 chance of getting it right. And so this can help us detect questions that have problems. Another parameter is discriminability, the gamma term here. And this gets multiplied by the difference between the skill and the difficulty. And so the more discriminative a question is, the better job it does of distinguishing good answers from bad answers. And you can imagine why places like the College Board want to have questions that are discriminative. This means that they can, if they have more discriminative questions, this means that they can ask fewer questions and do a better job of estimating an individual skill. Okay, so I won't go into the math of how you compute these things, but assume that you can get a bunch of people answering a bunch of questions, and you can compute the skill and difficulty, discriminability, feasibility, everything else for a whole bunch of questions. So one takeaway is that if you do this, you can get away with having fewer questions. So even if you agree that we should rank systems by their accuracy on these leaderboards, if you do an IRT analysis on even a smaller set of data, and so here the size of the data is getting bigger and bigger, bigger and bigger as you go from left to right, you do a better job of matching the true ranking of systems. And even more importantly, you can then look at individual questions to see where there might be problems. So here's a question. Why did the demand for rentals decrease? And so for this question, if you run the analysis, it says that this question has negative discrimination. So the smarter you are, the more likely you are to get it wrong. And that's because the question here is backwards. It's an incorrect question. It says that people are demanding higher quality housing, and it's saying that the demand for higher quality housing increased, which is backwards of reality. Here's another question that's ambiguous. And who did the Normans team up with in Anatolia? The only official answer is Turkish forces, but there are lots of other plausible answers here that could also be correct. And so by running this analysis, you can discover the questions that might be problematic. Then you can either throw them out or correct them, which is exactly what happens when people are developing, say, a standardized test. You have in-house testing. You see how people answer your questions, and you make sure that when you publish these tests, you correct as many of these issues as possible. Okay, so to wrap up, there are many places where Manchester and Cranfield overlap. And a lot of people can get by never thinking about the distinction about how you create these questions. And so if you just care about techniques, if you want to build a bigger transformer-based model to answer questions, do you really care about where the questions come from? As long as they kind of look the same, then maybe not. And likewise, if you want to build better resources for answering questions, like knowing that Paris is the capital of France is always going to be useful. And so you can build those knowledge bases without caring about this distinction. But if you want to understand users and how actual real-world people ask questions and search for information, then maybe you should focus more on the Cranfield paradigm. And if you don't want these unnatural, horribly complicated questions, you should stay away from the Manchester paradigm. So, but I think that there is a place for the Manchester paradigm. And even if you just use it as something that you want to stay the heck away from, the Manchester paradigm, I think, does help you do evaluations. And if you care about the evaluations and you want to increase fairness and representation, the Manchester paradigm helps you do that. If you look at natural questions, 2/3 of the questions, more than 2/3 of the questions are about men, and they're mostly about Americans. And so if you want more representation, then maybe you should have an unnatural distribution over questions from the Manchester paradigm, and explicitly encourage greater representation of underrepresented groups that aren't represented in the kinds of questions that the people who can afford smart devices currently ask. And so to wrap up, I think that if we recognize these two different paradigms and appreciate their different contributions to the way that people find information and fulfill their information-seeking needs, we can have the best of both worlds. And so regardless, I think people should think more about their data. Is your data for evaluation or instruction, or is it for understanding users? And I think once you answer that question, and many people have a clear answer to that question, then that can guide you to either Manchester or paradigm fairly obviously. And so the Cranfield data sets are big, and that's valuable, especially with modern machine learning techniques. But with that size also comes some imperfections. And so you might be able to train a system with many more parameters on Cranfield data than you might with Manchester data, but there might be hidden biases, ambiguities lurking in the data that could be recapitulated in your system. And so even if you want to use Cranfield data, you can use Manchester techniques to subsample, to filter, to curate the data to make it better. But regardless of which camp you land in, I think that we need to have more human evaluation of answer accuracy, that we shouldn't trust string matching to say whether an answer is correct. And many times we can, but like on a game show, if someone gets a question wrong, there should be a recourse to say, let's take a look at that. Let's bring a human into the loop and see if this is really the right way to evaluate this particular question. And for me personally, in the quest to build smarter computers, I am going to place my bet on the Manchester paradigm, because I think that its connections to education help inspire the way that we should build intelligence in computers like we build intelligence in humans. When a young child needs to learn something, we don't just throw them into a library and say, have fun, ask whatever questions you want, we'll check back in a decade. We have a system. We slowly ramp up the difficulty of the things that they learn. There is a curriculum. There are tests in this curriculum, and those tests are filled with questions written by experts to gauge where they are and to help elicit the kind of thinking that they need to do in terms of exercises, homework, and things like that to understand the world better. And I think that we can do something similar for computers, that we can use the Manchester techniques to craft questions that slowly increase in difficulty over time, that target the places where computers are currently struggling, and to probe where they fail using adversarial authoring techniques with the human in the loop to guide the data to where it needs to be to help computers fulfill the promise of Alan Turing and actually evince real intelligence such that it could fool a skilled inquisitor. Okay, and so again, I thank you for your attention. Thank you for the great questions thus far. I'm really hoping to continue this discussion. And what did I get wrong? What am I missing? This is still a relatively new idea. I'm trying to communicate this well, and so advice, tips, most welcome.
Can you see that first question there?
Yes,
Jordan?
yes, I'm reading it now. Yeah, absolutely. And yeah, so the question is, can you account for task-situated explainability? And I think I will answer the question that slightly differently. I think that the right way to do this is user-situated explainability. And so, yeah, as Cyril notes, that I, who am completely clueless about all sports, probably should have a clarification question asked to me if I typed in, when did Michigan last win the championship? I was probably asking about chess or the trivia competition, not football, and it's wrong for Google to assume that I care about football. Whereas if someone, yeah, is a complete football fanatic, they should get that answer. And so if you assume that the system knows whom they're talking to, these sorts of things are natural. If not, then we kind of need to move away from the one question, one answer paradigm and move more into a conversational paradigm, which is supported by both the Cranfield and Manchester setting, where in the Cranfield paradigm, you could have a follow-up clarification. Did you mean football? And since that's probably based on a population level analysis of people asking questions in the United States, probably what they're asking about. And then you could follow up and say, oh, no, I meant basketball, and in which case, then give the right answer. And this happens all the time in the Manchester paradigm as well. Just go to any PhD defense, and sometimes professors will ask questions with an ambiguity to test whether the student recognizes the ambiguity, and then they follow up. Are there any other interpretations of this that you should mention? As a hint to say, oh, hey, there's some ambiguity here. And so the split on Manchester versus Cranfield here is who is in charge of managing the ambiguity, the questioner or the answerer. Yeah, so so do the Manchester questions avoid some implicit bias? They avoid some biases, but not all biases. And so like this is still a problem. And so if you look at like demographic bias, the Manchester paradigm data sets are actually worse in some ways than the Cranfield paradigm questions. And so there's more of a bias in terms of asking about Americans and British people in those data sets. And there is a smaller representation of women, although most of that is explained by Cranfield paradigm questions having a lot of entertainment related questions. So it's complicated, but all of that being said, I think that we could, and so like this is a proposal that I wish would get funded. You could use some of the analyses to highlight for people in the Manchester paradigm when they are biased in particular ways to help guide them away from that. And that's something that's a lot harder to do in the Cranfield paradigm.
What other questions does anybody have? Anything? Okay, thank you, Jordan. That was just outstanding. Really, really, really enjoyable and super interesting. So we really appreciate your time.
Well, and thank you for the great questions, and I really appreciate the chat, and this is really fun. So thank you much for having me. And yeah, if anybody has tips or suggestions, please do reach out. Like, this is still very much inchoate, and every time I give this talk, I get a oh, you didn't mention this, and like, this is very much relevant. So like, please do reach out. There are lots of things I don't know, and so I would really appreciate any pointers, suggestions of stuff that I should be aware of.
I guess, Jordan, I do have one last question, which is, what are your next steps for this type of research? Are you doing other things, or?
Yeah, so on the adversarial data authoring thing, what I'm trying to do is I'm trying to work with professional trivia writing companies to show them what machine learning algorithms think about the questions that they're writing, so that they can write questions that are harder for computers. And so there, the sell is difficult. I also need to convince the professional trivia writers that this will help them write better questions for humans. And so this is the kind of thing that I'm working on right now. Another thing is to better estimate the difficulty of a question. And so right now, the only way that companies like ETS and the College Board estimate the difficulty of the question is by having humans answer the question. And so one thing that we're trying to figure out is, like, what questions are hard to answer? Can we predict that a priori from historical data to estimate when a new question comes in, is this going to be hard for a human to answer or not? And there are some obvious applications to education that come in here as well. Helping people study, helping professors write exams, things like that.
Fun, super interesting. I love the trivia part. You'll have to come back and next year and tell us where that goes and how it lands.
Absolutely, yes,
yeah.
And so for people who are interested, I have human versus computer trivia competitions on my YouTube channel, boydgraber.org, and so people can check that out there. And we just had a competition between Victoria Gross, who's the replacement for Ken Jennings on the Chase, take on students from my undergraduate natural language processing course. They created question answering systems, and it was an exciting game.
That sounds great. Thank you very much. All right, everybody. I'm going to just wrap things up here and say thank you for joining us for this really entertaining and interesting talk with Jordan. We will have one more, at least one more event this year. It will be April 14th at 11 o'clock. The speaker is TBD, but so keep an eye out for the announcement and the registration for the next talk. So thank you again for coming, and we'll see you again next time.